Hey guys, a couple days ago I had posted up some notes for formula writing and naming. I'm just going to go through some of the examples that were in there, as well as go through how to actually do them, in case you weren't quite sure from the content on the Moodle. So before we do that though, just one important thing. For a lot of these, there's one important file that you would need to get, or two technically, from the Moodle. There's obviously one, periodic table, right there, and there's also the table of common ions and numerical prefixes. And in that file, you'll find the charges for the different types of ions and the polyatomics that we talked about probably just before all the break things started. So those are important to have to do these. You'll kind of need that information to actually figure some of them out. So do make sure that if you're not going through anything else, at least make sure you go get those, because those will be important for solving a lot of these and figuring them out. Okay. So first things first, there was ionic formula writing. Just as a review, this part you probably would have done, sorry, back in grade 9. But in terms of figuring out the formula from a name, it's really not too bad. You really just have to look at the elements that are involved. So we have sodium chloride, for example, and using the periodic table, you'll find some information that you need to figure out how many of them are bonding together. So for one, sodium is in the first family, okay? So it has one valence electron that it wants to give up. Chlorine, on the other hand, is in group 17. Oops, a little messy there. Make these a bit bigger. Okay, and so it has 7 valence electrons. That means it's going to be looking for one more electron to gain, whereas sodium has one that it's wanting to give up. Okay, so remember, basically what's going to happen is sodium will lose its electron. Chlorine's got a very strong pull in them, and it loses it to that. Okay, so that means sodium, because it's losing that electron, is going to become charged, remember. So sodium will have a +1 charge, and chlorine, because it is gaining this extra electron from sodium, has one more negative charge than normal, so it is -1. And so when they come together, okay, they're quite happy together. They're in a 1-to-1 ratio. They complete each other quite nicely. And so you would have NaCl. And you only have one of each. So if you remember, you don't usually write the subscript if there's only one. It's kind of just assumed. So these ones, they work out nicely together. Next one, magnesium and hydroxide. So magnesium, it's in group 2, so it's got 2 valence electrons. Okay, hydroxide is OH. That is one that you would find in the polyatomic list. And if you do look it up, you would find it has a -1 charge. Okay, so it has one additional electron, and so it has more negative, a slightly more negative charge. Magnesium, when it loses its electrons, it ends up having a +2 charge. Hydroxide, on the other hand, is -1. Okay, so because of that, remember with an ionic bond, the charges need to add up to 0. They need to be able to cancel each other out because they're going to have those attractive forces to each other. But the thing is, for them to be bonding properly together, they need to cancel out. Okay, so if magnesium has a +2 charge and hydroxide has a -1 charge, we're going to need 2 hydroxides for every 1 magnesium to make sure those charges cancel out. What you may have done in grade 9 science is you may have done what's called a crisscross. So this one switches to there, that one goes down there, and our formula then is MgOH2. Remembering to put brackets outside the hydroxides to indicate that there are 2 hydroxides attached for every 1 magnesium. Okay. Now, a couple more examples. I'm not sure these ones were in your notes, but just a couple more just for practice. So for one, calcium. Okay, now if you look it up, it's in group 2, so it's got 2 valence electrons. Okay, let's make those bigger. Okay, but what that loosely is going to end up happening and translating to is the fact that calcium is going to lose those, and so it ends up having a +2 charge. Bromine, on the other hand, it's in group 17, so it has 7 valence electrons. Whoops. Let's just change that color there. Like so. Okay, so it's looking for one more, and when it does gain that one more, and oops, nope, not what I wanted, it's going to have a -1 charge. Okay, so again, the quick way is just to do the old crisscross, but again, what it really means is that, again, calcium has a charge of +2, so you need 2 bromines to cancel that out. Okay, so they switch, and you end up with CaBr dose. That's 2 in Spanish if you're not sure. So pretty simple. Okay, next one, potassium oxide. So potassium is in group 1. Oxygen is in group 16. So it has 16 valence electrons. Getting lazy with the colors now. Okay, so technically, potassium would have a +1 charge. Oxygen would have a 2 negative charge. So again, oxygen needs 2 more electrons. Potassium only has 1 to give. So there's going to be another potassium that you would need to have the required electrons for this. Okay, because they're both going to give them up. They're both going to go to this little oxygen guy over here. Okay, and so what that ends up meaning for formula-wise, we're essentially just doing this little switch. You have K2O, because you need 2 potassiums for every 1 oxygen so that they have the required number of electrons each. Okay? Now, moving on, something that would be new for grade 10 is that we look at the multivalent metals. So last year you probably would have skipped over this whole section, called them the transition metals, or that area anyways, and just left it at that. Okay? And you would have left them at that because these guys are a little bit weird. Okay, whereas atoms and elements in group 1, 2, and 15 on 8, 17, and all that on this side, they generally were pretty consistent. So everything in this first row here would have a charge of +1. Okay, everything in this column would have a charge of +2. Okay, on the other end, everything in group 17, for the most part, would have a -1 charge. I'm going to get rid of this here. Nope. Get rid of that, just so I have some more room. The things in group 16 would generally be -2. Okay, here we have -3, and so on and so forth. Okay, whereas these guys they're null, they're neutral, they're fine, they have no charge really. Okay. On the other hand, the thing with the transition metals is they're kind of all over the place. They just do, in some sense, whatever they want, really. Some of them, for example, like say iron here. Okay, iron can be +2, can be +3. Oops, that's a 4 because I can't. That's the number I was thinking of next. Okay. Pen doesn't want to agree with me. Okay, you can even get a plus, different numbers here. So the type that it ends up being is going to actually have an influence on basically the properties of how it reacts with other things, and it will also affect the name. Thing is, when you are doing chemical reactions, it is very important that you have the proper form. If you have the wrong form, you have a totally different chemical formula altogether, and that's going to influence how it reacts with other things, which means you might get a different product than what you were actually hoping for. Iron oxide can be two different things depending on which type of iron that is. So it is important that you do make sure that you do know what these mean and how they would respond with other things. So you have to be careful with those, especially if you were considering you were using these and say maybe you're pharmaceutical and you're making medications. You don't want to be screwing that up and using the wrong type or any type of building material. You want to make sure you have the same one. So let's take an example here using copper. Okay, copper can be either +1 or +2. Okay, so in that important document that I said at the beginning of the video, make sure you do get that because it does have the list of the different ones they can be commonly. Okay, so copper could be two different things. The way you tell is by looking at the one where we do have information on. Well, for example, chlorine is generally pretty consistent in that chlorine usually has a -1 charge. In this, if you notice, we only have one chlorine here. So that means the total negative charge is -1. Simple enough. Copper, if you look, we only have one of them. So that means the total positive charge available is +1. Whoa, they cancel out. That means this copper is the one with a +1 charge. So we would name it, copper 1 chloride. Okay, so this Roman numeral indicates the charge of the metal. Okay, it's not how many there are, it's what the charge would be. So whether it's +1, +2, +3, whatever it may be, that Roman numeral that's in brackets there is going to indicate the charge. Okay, probably a little bit confusing, so we'll do a few more examples just to really solidify this. So next one, copper oxide here. Is it +1 or is it +2? So again, like I mentioned, look at the one we do know about. So in this case, it's oxygen. Oxygen has a -2 charge. Okay, we only have one of them. So that means the total negative charge is -2. Copper, on the other hand, we only have one of them. Okay, there's no subscript there indicating that there is more than one. So that means the total positive charge would be +2. So these will cancel out. Okay, they add up to 0 like they should in an ionic bond. And that means the variety of copper is copper 2 oxide. Okay, let's move on to do some other ones here. Next one, iron 2, oh sorry, I just gave you the answer. Fe2O3. Okay, this one's a bit more complicated. Okay, there's oxygen, there's one we know about. Okay, so we will base it off that. So oxygen normally has a -2 charge. And based on this, we see that there are 3 oxygens for every 2 iron atoms. Okay, so that means the total negative charge then has to be multiplied by 3. So there is a -6 charge altogether. Okay, let's look at iron now. Iron's the other guy in this equation. I don't know, let's use green here. Iron. So like I said, it can be multiple things. It can be +2, it can be +3. But if you notice, there are 2 of them. Okay, so that means the negative charge that is being supplied by oxygen here, -6, needs to be canceled out by 2 molecules or 2 atoms of iron. So what you basically just do is divide this 6 by 2. Okay? And 6 divided by 2 is 3. I know there's a negative in there, but so that means they have to be +3. Okay, since you have 2 of them, your total charge then becomes +6. They cancel out. Everything's happy as can be now. They balance each other out. Hooray. So this would be iron 3, because it has a charge of +3, oxide. Okay. Now what you could also technically do, and this doesn't always work, it works a lot of the time. There's going to be a couple instances where it doesn't. Okay. So what you could really do is you could do what's called a reverse cross here. So take the subscripts, put them up there. Okay. So that becomes Fe3 plus. And this is 2 minus, which we know that checks out. Okay, and then that's essentially the same idea. But it is a good idea to understand how that works, especially because, like I said, there are going to be instances where that doesn't. Okay, so let's just make sure you do have the understanding of how that is here. So let's take a look at the next one, FeO. Okay, it's still iron oxide, but it actually uses a different form of iron. Because again, oxygen has a -2 charge. Iron, in this case, it can be +3, can be +2, but if you look at it, there's only 1. So our total negative charge is -2. All of that needs to be taken up and balanced out by this 1 iron atom that we have. So to do that, it has to be +2. If it was +3, there would be too much positive charge, and that would attract other oxygen molecules towards it, each iron atom, and that would throw off the balance, and that would not give us a 1-to-1 ratio like that formula suggests. Okay, so this then cancels out, giving us iron 2 oxide. Okay, again, just to stress, those Roman numerals is again the charge, not how many of them there are. That is a very common mistake. It happens even with my grade 11 chem kids or students and stuff. You need to understand that that is the charge and not the quantity of atoms. Okay, so there was a few more examples in your notes here. I'm not going to go over all of them, but these are the answers to the ones that are there. Feel free to send me an email or contact me through Teams if you do have questions about how I got those, but generally we're going to use the exact same process. Okay, so again, let's look very quickly right here. Nickel nitride. Okay, nickel can be different things, but nitrogen, on the other hand, has a -3 charge. There's only 1 nickel, so all of that has to be canceled out by that 1 nickel atom, so it has to be +3. Okay, we'll look at another one here. Oxygen, well known, -2. Gold can be a few different things, but we have 2 gold atoms. Okay, they are both attracted to this 1 oxygen, so that has to be divided amongst the 2 of them. So that means each of them are +1. They're each supplying a +1 charge to this to cancel out this -2. Okay, again, if you have other questions, just let me know, and I can help you out with them, but these are the other answers. Last little bit there was then going the opposite way, name to formula. This is a lot easier actually. Again, the big thing that you understand is that the Roman numeral for the 4th or 3rd time that I've been saying it is the charge of the atom it's involved with, so the tin. So this is telling us that tin has a +2 charge. Chlorine, on the other hand, tin is Sn. Because it has a +2 charge, chlorine, -1. Again, we do this little cross, but really what that means is there's going to be additional chlorines attracted to this tin to cancel out that charge. Okay, so that leaves us with SnCl2. We need 2 chlorines for every one tin to balance them out. Okay, lastly, just one more example here, tin sulfide. Okay, so there's that. If you don't know your Roman numerals, that's a 4. Okay, sulfide, That's sulfur, which has a -2 charge. And this titanium, based upon the Roman numeral there, has a +4 charge. So Ti 4+. Okay? So there are going to be multiple sulfurs attracted to this one titanium to cancel out the charges. Now what you could do is just do the cross and that works, or you could just see that there's a common multiple here. You would need 2 sulfurs to cancel out that, the +4. But if you do the cross, and this is why I say it's a good idea to understand because it won't always work, is you would end up with this, okay? And you want the lowest possible ratio. And so again, there is a common multiple between the between the 2 and the 4. Okay, so you actually would need to reduce this down to its lowest possible terms. So that, and I'm just putting them up there because my face will be in the other way otherwise, means we have TiS2. Okay, we would reduce it down. Okay, so that's everything there is for naming and formula writing. Please, like I said, ask me if you have questions, send me a message if you need. I'm going to post another worksheet for you guys to practice that has, I think, some answers onto it as well. But if you are taking grade 11 Chem next year, this is very important that you do understand this, because the stuff that you do in grade 11 Chem assumes that you already know how to do this part. So if you don't know, make sure you ask and don't just leave it and move on with your with things, because it'll help you if you are taking it next year. So that's all there is for now. Again, let me know if you got questions, and I hope you guys are doing well. I hope you guys are healthy and everything, and see you guys around.